We're going to deal with the concept of polar covalent bonds. So we know that if a covalent bond ends up sharing electrons between compounds, so if I take two chlorine atoms and I want to have a stable octet, I need to share the electrons. That forms a bond between the two. It creates the molecule, and each one of the atoms has a stable octet. However, in the case of something like hydrogen and chlorine, chlorine has 7 valence electrons, hydrogen has 1, will share the electrons and form a covalent compound. But if we look at the periodic table, one of these atoms wants to hog the electrons more than the other. So on the periodic table, if we look, fluorine is the most electronegative, and the general trend overall is as we head towards fluorine, fluorine wants to hog electrons more than anything on the periodic table. So in this area, typically they want to hog as well, and then this less and less, and then finally hydrogen way over here hogs much less than any of these other compounds. Atoms. So looking at the HCl molecule again, if we had an electron that wanted to, say, start here, it would come and hang out hydrogen a little bit, but then it would come to chlorine and want to hide out a little more and a little bit more. It would hog it over here and then back again. And so this is where you would most likely find the atom is on this side and very little on the hydrogen side. So much more hogging in this way. So what we do then is we'll actually draw an arrow that actually indicates from the hydrogen to the chlorine, I have an arrow, and I'll put a little line through it like this. The chlorine wants to hog the electrons more, so we're going to say that it has a delta minus overall. So if the molecule is neutral, one side hogs a little more, it's got a little bit more electrons on one side, it's a delta minus. And because the other side has less electrons most of the time, we're going to call it a delta plus. And the arrow indicates that. The arrow is pointing to the more negative side, and we draw the line through, which actually looks like a plus, and that denotes this side. So this arrow is called a dipole or a dipole moment. If we compare this to the chlorine atom above, we'll see that chlorine wants to hog the electrons, chlorine here wants to hog the electrons. Essentially, these attractions cancel each other out, so overall there is no net dipole of this molecule. This is just a covalent compound, and if there is a difference in electronegativity, a large difference, typically we call this a polar covalent compound. Now you may find in some textbooks it requires you may have learned in high school that there's a specific difference that's required. So if fluorine has an electronegativity of 4.1 and hydrogen has an electronegativity of 2.1, that overall this difference in electronegativity is 2.0 on some sort of scale. And I believe that the number is you want to be greater than 0.5 for this to be considered polar covalent. That's a textbook sort of number. It's a gradient, so it's more polar as it tends to hog the electrons more. It's less polar if it doesn't hog the electrons. So I don't like really putting numbers to it. But it's up to you if you decide you want to do that. And remember too that this is different than an ionic compound. So in the case of HCl, we're going to compare this to NaCl. In HCl, see we have the line that denotes that we're sharing electrons between the two. We're going to have a delta minus and a delta plus. So this is in the gas phase. The two atoms share electrons together, and this is overall there is a dipole here, like this. In the sodium chloride molecule, there is a full blown no sharing of electrons. Sorry. The electrons are given off wholly by sodium and given to the chlorine, and there is a positive and a full negative charge on each one of these atoms. There is a difference between these two. All right. So this is the polar covalent compound, and the reason why we really know that it's covalent is because we've drawn that line that shows that it's sharing electrons. This is an ionic compound, and in this case we don't draw a bond in between because they're not sharing electrons. They're attracted to each other because this positive charge and this negative charge allows these two to interact with each other.